an additional function that does not follow the original calling convention. So you are changing calling conventions. And to reason about that, we introduce what we called abstract protocols that materializes as an additional parameter in the simulation, in the relation. And we'll see in a moment how this can be used, particularly how this rule can be used. All right, so this is our methodology. Now, unfortunately, I don't have time to show the whole proof, but I have time to show the core of it. So I claim that the core of the proof is these two specifications. So the specification of the direct transformation and the DPS transformation. So the question is, what do we put here in these pre and post conditions? So for the direct transformation, this is straightforward. We just said that given two related similar values, calling mapd in both programs will yield similar values. So two functions return similar values, right? And this rule, this specification, is actually a specialized version of a marginal reasoning rule in the logic that you can see here, and that is stated more generally for any function. So now, let's see about the DPS transformation. For DPS transformation, as I've said, we change the calling convention. So in the specification, we said the following. We said that given two similar input values and the ownership in the target program of the destination, so given all this, map and map DPS in the source and target programs compute the same thing, the same values, and additionally, instead of directly returning it, map DPS writes it in the destination. So this is basically the essence of destination passing style. All right, and as before, this specification is can be derived from a more general rule in the logic that I have produced here, and actually both the former rel-dir rule and this new rel-dps rule, both of these rules are actually derived from a more general rule that I've introduced earlier, that is the rel protocol rule. And this rule allows to apply a protocol where a protocol basically represents a change of calling convention. Right. So in our case, in the TMC transformation, we instantiate this Chi protocol just by basically rephrasing the two specifications. So conceptually, this is essentially a co-induction hypothesis that is built in, that is internalized in the relation. All right. Now, I must also say that in the paper, you can also find other transformations that fit in this framework, that can be verified using protocols, so basically using this rule. And particularly, you will find the proof of an APS, accumulator passing style transformation, as well as an inline transformation. To conclude, we have implemented the TMC, the tail module constructor transformation in the OCaml compiler. We have verified its soundness using relational separation logic. And we verified other transformations using abstract protocols. Thank you.
Before lunch, anyone has a question?
Hi, thanks for the talk.
Hi.
So Similaris is a logic for concurrent refinement, and your language is sequential, if I understand correctly. Was that a problem? Did you just use the concurrent thing and ignored concurrency and it was fine, or did you have to do something there?
Indeed, it is sequential. We did not introduce concurrency, so say the full power of Similaris, because basically we wanted to just capture the essence of TMC. And TMC, tail module constructor, the transformation, does not involve any trick aspects regarding concurrency, I think. So we've not used concurrency. And I don't think this is, I think we could just add it in the framework just as Similaris did, and there wouldn't be any particular issue, I think.
Let's thank the speaker again.